Hello guys, my name is Sechanzi, Group 1. Our project title is Photo Voicing Accelerated Education Content Generation using Large Vision Models. So with large vision models, large language models like basically this is my technical reflection from the models, from a technical reflection from what I got from the last class or the last lecture. Basically, while large language models like GPTs are transformative with their underlying architectures and being fundamentally repurposed and often found lacking for low visual tasks, this likely informs our group's project, which aims to leverage artificial intelligence for visual storytelling. And basically, the key theoretical concepts and practical tools we have, basically it limits the texts. It has the limitations of text-centric models for vision, such as GPTs, BERT. Also, basically got the rise of large vision models and tools, basically the tools such as Unity for game development. We have Unity for game development. We have Blender for 3D image creation. Also, there was, among the insights from the lecture, was connecting AI to visual logic and 3D environments through using the existing open source models from Blender. Basically, combining with the artificial intelligence and version control from GitHub, basically with the help of the open source models from Hugging Face, as you see in the visions, with use of Blender to create visual images. Basically, in pick 1, you see an illustration of Blender, how it is used to create 3D images. Pick 2 shows a visual photo voiced image that shows a certain scene, and image basically shows Hugging Face, basically an open source tool ready trained models, basically with GitHub, that is used for collaboration. And image 4 basically shows Unity, a game development platform. The number 1 model I have is the Unity ControlNet. Basically, this is an all-in-one control text-to-image diffusion model, and it's highly relevant to the computational problem of the project, as this involves moving beyond pure text to image generation. The need for multimodal control, basically the practical application of large vision models for detailed controllable content creation. Basically, the domain-specific problem. The problem of controllable content generation focuses on producing images with fine-grained control over spatial layout, semantic content, and stylish guidance, unlike simple text-to-image prompts that enable structured, precise outputs. Supporting applications like therapeutic storytelling or visual aids where specific scenarios and emotions must be accurately conveyed. Basically, the computational problem of unit control net is that unit control net solves controllable content generation by combining text prompts with local and global conditions to produce high-quality images built on stable diffusion, which it fine-tunes lightweight adapters for efficiency, ensuring minimal parameters. Basically, unit control net is applied in a way that for a project aimed at generating visual structured narratives, I would use unit control net architecture as a blueprint. And basically, the pipeline would be an input, basically a written story segment, a text prompt, and a hand-drawn storyboard frame that may be a sketch condition and a chosen style of reference. Basically, processing of the input involves feeding these into the pipeline built on the stable diffusion and fine-tuned in the unit control net adapters. And basically the output is a high quality stylistical consistent image that accurately depicts the scene described in the story and laid out in the storyboard. Basically, this is the system architecture. This is the visual architecture of the unit control net pipeline. And basically, we see the input conditions, basically local conditions, that is the kernel, depth, pose, etc. There is text inputs. Then after inputting text, it can be noise. You see a noise predictor of the unit control net, or the global it can also go to the global control adapter through the text tokens, and basically extended prompt via a close attention, then to the output, that is an image faithful to all inputs. Basically, the image produced is a representation, basically, of the text that was input at first as the input. The second model is segment anything model, and this is fundamentally relative to the computational problem at the heart of our project. We focus on moving beyond pure text to image generation, and the need for visual logic and application of large visual models for controlled story-driven content creation is directly addressed by the capabilities of segment anything model 7. And basically the domain-specific problem here, the problem of general purpose visual understanding and isolation focused on open world codable segmentation and identifying and isolating any object based on user intent. This enables dynamic image querying for storytelling and structured outputs, aligning with SAM's ability to handle high-level ambiguous instructions. The computation problem is that SAM tackles profitable segmentation by combining an image encoder, prompt encoder, and mask decoder to generate high-quality masks, spatial text, and mask prompts, and it also ensures speed, ambiguity, awareness, and strong zero-to-shot generation, enabling real-time flexible object isolation. Basically, the goal is not to perform a single predefined segmentation, but basically the task, an example of the task is just segmenting people's cars, but to build a system that can identify and isolate any object or region in an image based on users' intent expressed through a single prompt, and this is often referred to as open world or promptable segmentation. Basically, an example, there shall be inputs that will be an image and a prompt. Under image, under segmentation, under segment anything, basically, there shall be an image and a prompt. A prompt can be of several types. There can be special prompts or text prompts or mask prompts, and basically the output can be one or more high-quality segmentation masks corresponding to the object specified by the prompt. Basically, the model architecture, the architecture of segment anything model, and the core constraints are generally speed, ambiguity, and awareness, and the architecture decomposes of three models, that is the image encoder. This is a heavyweight vision transformer that processes the image once to create a high dimension embedding. And we also have a prompt encoder. This is a lightweight module that encodes the various types of prompts, that is points, boxes, and texts, among others, into vector representations. We also have a MASIC decoder, and this is a very lightweight transformer-based decoder that efficiently combines the image embedding and prompt embedding to predict output masks. Basically, segment anything deals with objects reversing pixels, and basically these pixels are a color of dots. So, image segmentation basically is the process of partitioning digital images into multiple segments. Those are sets of pixels or objects. So as you see our architecture, the visual architecture, first of all, we have prompt, we have the input. Basically, the input can be an image that is input into the heavyweight image encoder that can be a vision transformer. And this processes once per image, and then the next step is image embedding, and basically it is in a lightweight mask decoder, and it is a transformer based and predicts in 50 milliseconds. That is the output masks. We have the prompt processing phase where we shall have a spatial prompt. You know, this takes in prompts of several types. We have a spatial prompt. These are points. These points or a box. This can be in form of points or box. We have the text prompt and the mask prompt. The spatial prompt can go to the prompt encoder, and the text prompt can go to the clip text encoder. Then the mask prompt can go to the CNN encoder, and all of them are combined in the prompt embeddings that later joins them to the lightweight mask decoder. The other is visual instruction tuning model. Visual instruction. This directly and profoundly relevant in a way that it, due to our project basis, it aims to create an intelligent system that understands a complex multi-step education topic. And that's an example. We say a topic about how to grow maize, and it can generate coherent visual narrative sequence to explain that topic. And this is quite essential visual instruction following a task. For the following visual instruction following task. Basically, the domain specific problem in the review is the project's problem is the slow and costly creation of accessible educational visuals, while Lava addresses limitations of earlier multimodal models by enabling complex instruction following capabilities. With visual context, surpassing models like BLIP2, Open Flamingo in tasks such as explanation and anomaly detection. Computation problem definition, Lava tackles vision language instruction following using CLIP and Vicuna with efficient alignment, while the project extends this to generate coherent, accurate, efficient education storyboards. Basically, visual instruction tuning is based in Lava, that is large language and vision assistant. This involves teaching an AI to follow instructions about visual content, similar to how large language models follow texts valued on large data sets of high quality pictures with paired conversations about them. And basically, this model demonstrates a foundational capability where the system requires, i.e., connecting high-level abstract instruction with grounded visual understanding and generation vision. Basically, visual instruction tuning architecture. So, first of all, there shall be an input that will go to the visual encoder, that is CLIP VIT. Then it goes to the visual features, then the projection layer, that is a trainable linear. Then it creates visual tokens, and basically text responses are made. So we also have text instructions. As the input image, there is also text instruction. Then word embed, they are taken to the word embedding layer and form instruction tokens that are concatenated and up to the large model vicuna that is frozen to a text response. The other is instruct pics to pics. This paper is also relevant to our proposed work as it provides a foundational computational framework for translating high-level instructional intent into a visual output. And basically, our project's core challenge is to interpret an educational topic. For example, a topic, let's say how to grow maize, and generate a sequence of images depicting that process. And this is a direct extension of instruct pics to pics. To interpret an instruction and generate a single edited image that fulfills the instruction. And the domain-specific problem, the project's challenge is costly, expert-dependent creation of educational image scenes, while instruct pics to pics addresses the gap in intuitive high-level image editing by enabling fast general-purpose edits without inversion masks or fine-tuning, making real-time applications practical. Basically, the computational problem, instruct pics to pics addresses instruction-based image editing using conditional diffusion, while the project extends this to instruction-based image sequence generation, and the focus shifts to producing factually accurate, pedagogically aligned and sequentially representative visuals. And instruct pics to pics basically addresses a problem, the lack of a model that is capable of performing general purpose image edits based on intuitive high-level instructions, that is, and rather low-level description of the target image. For example, a photograph of a king with a gold crown. Then the architecture. Instruct pics to pics architecture and pipeline. First of all, there is data generation. We have the data generation pipeline that involves human written captions on an image. They are fine-tuned in GPT-3. And also it involves a text pair, that is text to image pair with stable diffusion. Stable diffusion basically is used in generation, is a model used to generate images in Blender, so it can generate image A and image B. Then a text pair to a tab to the conditional unit control net that is denoised to produce an edited image. And instruct pics to pics training model that is used to, that is where an image is input, that is where images are input with text instruction, pair-to-pair image. It's a pair-to-pair an image with text instruction, which in turn, that involves a number of images, maybe thousands, hundreds of thousands of images in pair-to-pair with text captioned on them for training a model that in turn is able to produce a latent representation with the clip text encoder. Learning transferable visual models from natural language natural language supervision. And this paper basically is relevant to the education content generation system, as it provides a foundational vision language model that can understand and generate semantically aligned image text pairs, which is central to automating the creation of narrated visual storytelling sequences from education topics. And the domain-specific problem, the problem is automating education content generation by transforming a text topic into coherent image sequence with synchronized narration, requiring semantic understanding, pedagogical accuracy, cultural relevance, and efficiency in low resource and multilingual context. The computational problem involves transforming a natural language topic into stepwise images with synchronized narration using natural language processing decomposition model, generative image models, TTS synthesis, and clip-based alignment, while ensuring low latency accuracy, cultural relevance, and multilingual support and minimum human. Basically, the pipeline architecture it involves transforming a high-level education topic into a sequence of illustrative images, ensuring native coherence and instructional accuracy across steps, and synchronizing visuals with natural language narration, operating effectively in low resources and multilingual latency settings. Basically, the pipeline architecture, first we shall input educational topic. The second step is natural language processing module for step decomposition. Step one, first of all, an example shall be step one, prepare soil. Step two, plant seeds. Step three, okay, step N, harvest maize. Then a clip guided image generation. So those image generation that will represent those sequences, generated image sequence or TTS narration scenes, and the output will be a narrated visual story, just a visually narrated story in the form of a visual image. Then the unified multi-modal generative, this is a combination of all the five peer-reviewed papers, where all the five peer-reviewed papers from which the models were gotten. And this is directly relevant to the project since it provides a comprehensive technical blueprint for building an end-to-end system that converts education topics into narrated visual stories. And this architecture integrates the very capabilities of our project. Basically, the domain-specific problem is generating coherent, accurate, and relatively synchronized educational visuals from topics optimized for low-resource, multilingual, or low-latency environments. The computational problem is designing a low-footprint multimodal system that transforms a natural language topic into culturally accurate multilingual image sequences with synchronized narration using Lava, large language visual assistants, segment anything model, unit control net, instruct pix to pix, clip, and TS. So this is the architecture where we shall input educational topic, which is shared to a text encoder. So Lava will aid in instructional decomposition. So step 1, it will be text, step 2 text, and step n text, and unit control net plus diffusion encoder, and it will there will be a generated image sequence. The next step will be optional editing and refinement. That is segment anything model for segmentation and instruct pix to pix. The output will be in narrated visual story. That's all.